So today we're looking at Snell's law and what happens when light goes from one medium into another medium. Last class we learned that light is a special type of wave called an electromagnetic wave because it's made of electricity and magnetism. Electromagnetic waves are transverse waves that don't require a medium to travel through. They all travel at the same velocity, which is the speed of light, or 3.0 times 10 to the 8 meters per second. And this is the speed limit of the universe. There's a large range of different frequencies of electromagnetic waves, and this is called the electromagnetic spectrum. So today we're going to take a look at refraction, which is how light changes direction upon entering a different medium. We'll learn to solve these types of problems using Snell's law. When a ray of light contacts a surface, some of the light will bounce or reflect off the surface, and some of it will go into the surface. The law of reflection just says that the incident angle of the incident ray, measured from the normal, will equal the reflected angle of the reflected ray. It's important to note that both of these angles are measured from the normal. The light that enters a new medium changes its direction, or angle, and changes its velocity. The speed of light is constant in a vacuum, but it will slow down when it enters an optically dense medium. So that means that light travels slower in water than it does in air. Each medium is given a constant called its index of refraction, which basically explains how quickly light moves through that medium. This constant is a ratio of the velocity of the light in the vacuum, which is c, the speed of light, to the velocity in the new medium, v. So the equation is that the n in any medium, could be in water, is equal to the speed of light, which is c, or 3.0 times 10 to the 8, the speed of light in a vacuum, divided by the speed of light in that medium. Now, since the fastest velocity is c, the index for a vacuum would be c divided by c, which would be 1. And for all other media, you get a ratio that's greater than 1. The larger n is, the more bending, the slower light will go in that medium. Okay, so here's an image of what happens. Let's say I have water here and air here. So as my light beam travels through air, what happens when it hits the water is that some of that light reflects off the water. That's why you see reflections in the water of things like trees in the sky, clouds. And the angle that it comes in is called the incident angle, theta I. And that incident angle is the same as the reflected angle. So those two angles are the same. But also when light hits the water, some of the light is going to go into the water itself. And this is called refraction. The light bends, and you get a refracted angle called theta R. And again, both of those angles are measured away from the normal. Okay, and the word normal means perpendicular, because it's a line that's 90 degrees with the surface. And this is the reason why when you look at a cup that has some water in it, and you have a straw sitting in that cup, it kind of looks like the straw is broken or bent at the surface. And there's a relationship that we can use to calculate how much that light gets bent when it goes into a new medium. So let's imagine here that we have light that's traveling from something like air to something like water. The light slows down as it enters the water. Let me use red for air, actually. Okay, so what happens is that the light is traveling through air at about 3 times 10 to the 8. And as soon as it hits the water, it's going to slow down. And because it slows down, the light bends, because the two light rays are always going to travel parallel to one another. Because it's going slower, we need to change the angle. So what happens is that on any given point separating these two waves, the 90-degree line here, these 2 points are traveling at the same speed downwards towards the surface of the water. They cover the same distance in the same time. So what happens is when this first point hits the surface, it's going to immediately slow down. But its corresponding point is still traveling at the fast speed. And basically, because it's going slower, it's going to go slowly and cover this short distance, while the second wave, the second ray, is covering this distance here. So the first ray will come to the surface, while the corresponding point on the other ray still has a bunch of catching up to do. As soon as that ray hits the surface, it's going to slow down and cover a shorter distance, and by the time it's gone that short distance, the other ray will have caught up. So let's label some things here. The angle away from the normal as it's coming in is called the incident angle, theta I. The angle away from the normal on the other side is called the reflected angle, theta R, refracted. We can also find those angles inside of these triangles here. If you take a look at this triangle, you can see that theta I is also right over here. And if you look at this triangle right here, you can see that theta R is also right here. Now, because sine theta, SOHCAHTOA, is opposite over hypotenuse, that means that the opposite side is hypotenuse sine theta. So the opposite side of the angle is hypotenuse. Let's call the hypotenuse x in this case. Hypotenuse sine theta. And that's this distance right here. Okay, the opposite side of this angle is hypotenuse, which just happens to be the same, also x. This distance is hypotenuse sine theta r. And because these two rays have to travel parallel to each other, hypotenuse sine theta I is the distance on ray 2 in the air, and hypotenuse sine theta r is the distance on ray 1 in the water. And because these two are traveling parallel to each other, this has to happen within the same time, so that ray 2 can catch up to ray 1, so to speak, and travel parallel to it as they continue going downwards. So since velocity is distance divided by time, that means that time is velocity over distance. So the time in the air will be the same as the time in the water for those two parts. So the time in the air is the velocity in the air divided by the distance in the air. And the time in the water is the velocity in the water divided by the distance in the water. So the velocity in the air is going to be fast. That's almost the speed of light. The distance in the air is this one, the hypotenuse sine theta I. The velocity in the water is going to be smaller. Light travels more slowly through water. So does sound. That's why if you talk underwater, it sounds really cool. hard to make out what people are saying. The distance in the water is this one. Hypotenuse sine theta r. And now if I just do some fancy cross multiplying, I get x sine theta r times the velocity in the air is x sine theta I times the velocity in the water. Since x is the same, I can cancel those out. So sine of the refracted angle times the velocity in the index is sine of the incoming angle times the velocity in that's refracted. Now from above, by the definition of n is c over v. So if I want to write this in terms of n, I could use vi equals c over ni. So instead of vi, I could write c over ni, and instead of vr, I can write c over nr. Now I don't like fractions, so I'm going to multiply nr onto this side, so it's not in a fraction, and I'm going to multiply ni onto this side. And I've got c's on both sides, they can cancel. So I get Snell's law, that the index of refraction times sine of the refracted angle is equal to the index of refraction for the incoming ray times the sine of the incident angle. And that is called Snell's law. You don't need to know how to derive this law. So you don't need to know all these steps that I told you here. I'll give this to you on a formula sheet, and you just need to know how to use it to figure out how much light is bent in different situations. So let's take a look at some examples. So Snell's law states that for a light ray traveling from one medium to another, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. This constant is just the ratio of the different indices of refraction. And here's some common indices of refraction. So in a vacuum, n is 1. In air, light travels almost the same speed as a vacuum. It's very close. In water, light travels much slower, n is 1.33. The bigger the number is for the index of refraction, the slower light travels in that substance. And this is a formula that you need to know how to use. And remember that light always bends towards the normal when going from a low to a high index of refraction. So low would be something like air, high would be something like water. So when it goes from air to water, the incoming light is going to have a larger angle in the air and a smaller angle in the water. It's going to bend towards the normal. So first example, we have light coming into contact with the surface of a pool. So we've got some water here. And air. I'll always draw the normal line, which is just a 90-degree line to the surface. So we've got some light coming in, and the light coming in is coming in at an angle of 35 degrees. Okay? And when it hits the water, that light is going to bend towards the normal. So it's going to come, and the angle is going to be closer to the normal line. We want to know exactly how close. What is that angle? So let's write down the indices of refraction here. N for air is 1.0003. And N for water is 1.33. So now I can set up my equation using Snell's law. The incident index times sine of the incident angle is the refracted index times sine of the refracted angle. So the incident index would be the air, 1.0003 times the sine of the angle in the air is equal to n of the water times sine of the angle in the water. I'll give it theta w for angle in the water. So you need a graphing calculator from this. You got to make sure that your calculator is in degree mode. So go into your mode, change it to degree. It won't work in radian mode. So we're 1.0003 times sine 35 to get 0.57. And I really have to keep all the decimal places if I'm going to get the right answer. Okay, now this means 1.33 times sine of theta w. So in order to move the 1.33 to the other side, I've got to divide both sides by 1.33. I'm just going to do that now. Divide by 1.33, get that on the other side. So I get 0.43 equals sine theta. And again, I'm going to keep all those numbers. Now the problem here is, how can I move the sine to the other side of the equation? In this case, sine theta w does not mean sine times theta w, but it means sine of theta w. You can't just divide sine on both sides. Instead, you need to use a function that's going to cancel off sine. So in order to cancel off sine from one side of an equation, I need to use the opposite of sine. And the opposite of sine is sine inverse. If I do sine inverse on both sides, then sine inverse and sine cancel. So whenever you're trying to solve for an angle, you're going to use the sine inverse. You push the yellow button and then sine, so you get the sine inverse. And then we're going to plug in all those numbers, the answer, 0.431389, to get the angle, 25.555 degrees. And with 2 sig figs, I'm looking at an angle of 26 degrees. So in air, my angle was 35, and now it's bent much closer. Now this angle here is 26 degrees. Okay, a diamond is dropped in a pool of water, and light from the water enters the diamond. I've got this pretty diamond here, and it's sitting in a bunch of water. So on the top I have some water, and then I have my diamond. So I've got light traveling from the water. It hits my diamond, and when it hits it, it bends towards the normal. So I need to draw the normal line, which is just a straight line perpendicular to the surface. And it's saying that the refracted angle is 25 degrees. So that means after it refracts, this angle is 25 degrees. What is the angle of incidence? The angle of incidence is the angle that it's coming in at. So N for water is 1.33. Saw that in the last problem. N for diamonds is 2.42. So I take my N for diamond times sine of the angle in the diamond, and that's going to equal my N for water times sine of the angle in the water. So N for diamond is 2.42. Sine of the angle in the diamond is sine 25. N for water is 1.33. And sine, I'm trying to find the angle in the water. So I'll take my calculator. Well, why don't I do this in one step this time? So I want to solve for the angle. I'm going to divide both sides by 1.33 to get that number on the other side. So I'll go 2.42 sine 25 divided by 1.33. And that gives me 0.7689. I'm going to keep all the decimal numbers. And now I want to solve for theta. I can't divide both sides by sine, that doesn't make sense. I have to get the sine onto the other side of the equation by using the opposite of sine, which is sine inverse. Those cancel. And I'm left with sine inverse of 0.768, which is 50 degrees. And when light travels from a more optically dense to a less optically dense medium, so from maybe water into air, from a high end to a low end, it bends away from the normal and towards the surface. The incident angle is now less than the refracted angle, and if you continue to increase it, you can make the refracted angle approach closer and closer until the refracted ray is actually parallel to the surface. The special angle when this occurs is called the critical angle. Any incident angle greater than the critical angle causes all of the incident light to reflect back into the incident medium. This is called total internal reflection. So this is what happens when you're starting in the more dense medium. So in this case, if we took a flashlight underwater and we shone light from under the water, what happens is that the angle between that incident ray and the normal will become bigger when it leaves and goes into the air. Okay, the light will bend away from the normal. And the bigger that we make the angle through the water, if I keep increasing this angle here through the water, the bigger the angle it will be away from the normal. Until eventually, this light is going to be actually parallel to the surface of the water. And if your eye is somewhere above the surface of the water, you're not actually even going to be able to see that light that's traveling right along the water side. So we want to find out what angle does it take so that when the light comes in, the light that goes out is exactly parallel to the surface, that none of it escapes. That's the critical angle. What happens at that point is that instead of refracting, all the light is pretty much reflecting at the same angle that it went in the first place. That's called total internal reflection. So this follows the same principles that we had before. Take your N in the water, take your N in the air, and this time what we want is N in the water, sine of the angle in the water, is N in the air, sine of the angle in the air. So N in the water is 1.33. And we want to find out what angle do you need in the water so that when it goes into air, the angle will be, the light will come out parallel to the surface of the water, that the angle will be 90 degrees. So when you're looking at a critical angle problem, you want the outcoming ray to be at 90 degrees to the normal, right along the surface. So again, to solve this, we can divide both sides by 1.33, get the coefficient to the other side, and you get 1.0003 sine 90 divided by 1.33, which is 0.75. Okay, same thing as before. We want to move the sine to the other side, but not the angle part. So we're going to use the opposite of sine, which is sine inverse. That'll cancel the sines on the left-hand side and leave us with sine inverse of 0.75, which is 48.7 degrees, or 49 degrees. Okay, so what that means is as long as your angle in the water is at least 49 degrees away from the normal, that all of it's going to reflect. If you have 50 degrees or 80 degrees, and you're shooting light through water, all of the light is going to reflect and none of it is going to come out into the air. You can kind of test this if you just take a glass of water, a nice glass. Well, actually, you can take an empty glass first and just sit it on a table, and underneath the table, or right on top of the table, put a penny. Okay, so you got a glass, penny on a table. And just put the glass right on top of the penny and then fill the glass with water. And you'll see that from certain angles, the penny disappears. That you can't even see the penny because the light from the penny is being completely reflected because of the internal reflection that's happening due to the glass and the water. Okay, now the other way around. A block of glass has a critical angle of 45 degrees in air. So this time we've got some glass here. We're shining light from the glass, and the light should escape and get further away from the normal. But because it says that the critical angle is 45 degrees, what that means is that when we shoot it at the light through the glass at 45 degrees, that none of that light is going to escape. All the light is just going to travel right along the surface of the glass. None of it will be refracted. All of it will be reflected at 45 degrees. Okay, and the refracted light will be parallel to the surface. So we've got to look up the N for glass. N for glass is, oh no, we need to find it. We're trying to find the N for glass. What is the index? We don't know. But we do know the N for air. N for air is 1.0003. So N air, sine of the angle in the air, is N glass, sine of the angle in the glass. N air is 1.0003. For critical angles, the refracted light will be going out at 90 degrees. And the angle in the glass is 45. So 1.0003 sine 90 is 1.0003 because sine 90 is 1. Sine 45 is 0.707. Now to solve for the N of the glass, now we've got N of the glass times 0.707. We're going to divide both sides of the equation by 0.707. 1.0003 divided by all those decimals gives 1.4. The index of refraction in the glass is 1.4. So your homework is to do the worksheet that is attached to Edmodo to practice Snell's law. Numbers 1, 2, 4, 5, 7, and 8. You have a quiz tomorrow on everything that we've covered in waves, but not today's lesson. This quiz will be multiple choice and is mostly going to focus on the vocabulary. So you need to know things like what is amplitude, what is refraction, diffraction, reflection, phase, all these different vocabulary words. And also how to use some of the equations like T is 1 over F and V is lambda F. That's all.